Okay, welcome back. We are beginning our third theme today, which is on interpolation. So we are going to interpolate various functions by means of polynomials. So we will first of all see the need for interpolation, and we will also see why polynomials are important and why we would want to interpolate using only polynomials. Um, so this is our 10th lecture, and we are now beginning it with this very nice and something which is very basic really. So this is the census data of our nation. So after we got independence in 1947, then right from 1951 we have been conducting our own census, and 2021 I think is delayed because of the pandemic, but the data up to 2011 is available. And so it's very interesting to see this. So for instance, we had 36 crore 10 lakh and 88,000 in 1951. You may say 36 crore 11 lakh almost, and that went to 83 crore 86 lakh in 1991. Then we crossed 102 crores in 2001, and 120 crores were crossed in the last census, which is in 2011. So the census is taken every 10 years, but supposing you wanted to know what was our population in say 1983. So 1983 is a very important year for all cricket lovers. And suppose you wanted to know an estimate of the population. So of course it would be very difficult to find the exact population in 1983. And it's also not clear when, meaning what day you are looking at. But let's say that in the year 1983, we would like to know what is the estimate of this population. Then the best thing would be to take these points. So you have these points 1951 up to 2011. Then there are these values. So you plot them on a plane. So there is the x variable, which is the year, and the y variable, which is the values. And you try to fit a function on those points. So those will be some points given in the plane, two-dimensional plane, and you would want to fit a function to this data, which a function which fits to all these data as best as possible. Okay, and once you have this, then you can simply compute the value of 1983 of this function, and that would be one reasonable estimate. So the function, if your fitting function or the interpolating function, this would be the function which is interpolating. So if you had a better interpolating function, then you would get a better estimate. All right. So this is why interpolation is very important. And typically what we are going to do is that once we have some function, remember a function need not always be given by formula. It could be given just like we have given it here, where you have some values of x and then there are some values of y. That's a function for mathematician. So whenever we have a function, we would like to interpolate it by means of a formula, so to say. Okay, so that's what we would want to do, and one of the best ways to do that would be to use polynomial functions. Why would that be the case? So on earth, polynomials are one of the most useful functions. These are the most well-known functions that we have. These are functions of this form. Typically we would write it as px, qx, or rx or such, and they have the form a sub n x power n plus a sub n minus 1 x power n minus 1 plus dot 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 plus a1x plus a0. If you are working with real numbers, then these ai, a1, a0 up to a1 up a0, a1 up to an, these are all real numbers. Okay, so this is what we have as a polynomial. Why are polynomials important? That is because they uniformly approximate continuous functions. What it means is that whenever you have a continuous function from such an interval AB to real numbers, then there is a polynomial which is as close to the function as you want. What it means is that if you draw the graph of this function f and draw the epsilon neighborhood of the graph, so it would look like the river that we would draw when we were children. So it would be you are fattening the graph of your function by epsilon on both sides. So you would have that epsilon neighborhood of the of the graph, then there is a polynomial whose graph lies in that epsilon river. That's what we mean by this result. And that means that for any point on this interval AB, the function value and the polynomial value do not differ by more than epsilon for any point on that interval. And you can take this interval as large as you want. Okay, so this is what is the Weierstrass approximation theorem. And how would you compute these polynomials? Well, Weierstrass did not tell that. He left it to some other mathematicians. But now we have some constructive algorithms to compute these polynomials, and perhaps we will see them in our course. But we will take this as a motivation at the moment to study polynomials. So that's why this is one reason that polynomials are very important and very useful. Another reason is that whenever you take a polynomial and take its derivative, you get one more polynomial. So derivatives of polynomials are polynomials, and therefore several computations with polynomials become very simple. We have seen that in Newton-Raphson method, we have to compute the derivative. If you modify it, you have to compute the second derivative and so on. And polynomials are typically, once you compute the powers of the given point, then you can just add them, and the computations are much more simple than doing sine function or exponential and so on. So this is why polynomials are the most nice functions, and we would like to approximate given functions by polynomials. But how do we find these polynomials? And so you may remember from our very first lecture that we had used Taylor polynomials. So what were these Taylor polynomials? These were given by Taylor's theorem. And they said that whenever you have a point, at that point, your function can be approximated by Taylor's theorem. So in a neighborhood of your point, you can approximate your function by those Taylor polynomials, and there is an explicit error that can also be given. But one very important point is that these Taylor polynomials will approximate your function only at that point. You don't know what's going to happen when you go away from that point. So for instance, if you consider this function e power x and take the first 6 Taylor polynomials, they will be p0, p1, p2, p3, p4 and p5. So those are the first six Taylor polynomials, the 0th one, first one, second one, up to 5th one. And you know what those polynomials are. The p0 is just 1, p1 is 1 plus x, p2 is 1 plus x square by 2, p3 is, there is an x cube by 3 factorial term, and then p4 and p5. So we know what these 5 Taylor polynomials to the function exponential of x at x equal to 0 are. You can in fact write down all of these. Okay, and let's see how they approximate your function as you go away from the point 0. So here we see that our blue curve is the curve y equal to exponential of x, and just above the x-axis we see a horizontal line which is given by the function y equal to p naught x. It is y equal to 1. P naught x is the constant function 1. That's why this line is horizontal. The graph of this constant function is going to be the horizontal line. Above this horizontal line, we see a graph made of dashes. That is the polynomial y equal to p1x, 1 plus x. It is that particular line. That's also a line. It's a linear polynomial. So that will be a line. Above that, we have the dotted line, and that's the quadratic polynomial p2x, which is 1 plus x square by 2. Above that, once again, you have a continuous graph, which is y equal to p3x, then one with dashes, which is y equal to p4, and then one with dots with y equal to p5x. So definitely, if you were looking at y equal to p2x, by the time you reach x equal to 3, the value of the exponential and the value of your p2 are very far away. And it might seem here that as you are taking higher and higher Taylor polynomials, then you are getting better approximations. But that will not happen always. So for instance, let's take this example at the other extreme. Other extreme, because exponential function is one of the Very nice functions, although it's not a polynomial itself, but it's not that bad compared to polynomials. In fact, it's a limit of polynomial function. So exponential function behaves very well with respect to polynomials, but this is the function 1 upon x, which is defined away from 0, and you can compute its Taylor polynomials at x equal to 1. These are the Taylor polynomials. And suppose we compute the value at 3 for our function, it will be 1 by 3. But if you compute the values of these Taylor polynomials, you will see that you are getting 1 minus 1, 3 minus 5, 11 minus 21, 43 and minus 85. So these values are going to infinity. This is the divergent sequence Pn of 3. And so 1 by 3 is not achieved anywhere here. So what is going wrong? The thing that is going wrong is that something that I have already said, which is that the Taylor polynomials use information only at the given point x0. So you may have the function value at x0, all its derivatives at x0, and then further derivatives at x0 only at x0, but we don't worry about other points. That is one problem, which is why Taylor polynomials don't approximate our functions nicely. So therefore, for ordinary computational purposes, it would be more efficient to use a better data. That means you should have information at various points and then try to interpolate that data. This is what we should try to do. You know, for instance, if you had the information about the census of our nation only for 1951 and then 2011, then getting the value at 1983 in a reasonable way would be very difficult. But having the value at each 10 years interval gives you a much better understanding of how the whole function evolves, how the population is evolving. So having a more data is always important. This is what we are going to do in the remaining part of the theme. This is not to say that Taylor polynomials are not useful. In fact, we have already used them for some computational purposes in the approximation and so on. So they have already been used and perhaps they will again be used. Okay, so that brings us to what are called Lagrange interpolating polynomials. So we will actually derive a very nice formula for writing down polynomials which interpolate the data of n points and their n values. So let's start with some of the very basic situations, which is that you have a function which is defined on a point x0 and the value is y0. Then is there a polynomial px with px0 equal to y0? Do you have a polynomial in one variable whose value on x0 is y0? Now one can write down several polynomials naturally. You know, you just want to have a polynomial whose value on that particular point is some particular thing. But the simplest such thing would be perhaps just the constant polynomial. You can get many polynomials, definitely. You have some polynomial, suppose you have your polynomial y equal to x square, which is the parabola, and you pull the parabola down or right or left and make sure that it lands on this point x0 comma y0. Then you would have a second degree polynomial passing through the point x0 comma y0. Or you could do the same for any degree polynomial. But one of the simplest things that would work is the constant polynomial. So while trying to get polynomials which interpolate our given data, we would also try to get the simplest one. We don't want to use too much of computer time. Computer time is going to be expensive for us. That's our currency in this course. And we do not want to spend too much of computer time to do this all calculations. So we would look at simplest polynomials, and given a point x0 and its value y0, the simplest possible polynomial that you can think about would be the constant polynomials. This is the polynomial whose graph will be horizontal, just like we had that p0 equal to 1 as the first Taylor polynomial, zeroth Taylor polynomial for exponential function. This graph will also be horizontal. It will pass through x0, y0, but at any other x, the value will simply be y0. This is what it will do. At every point x, it will have the same value, which is y0. Okay. So once having cleared this thing, in mathematics, it is also very important to do some of the most initial cases. So once you have done with the initial cases, only then you can build some theory for the higher cases. And that's what we are going to do. So after done with this case of 1 point and its value, we now take 2 points, x0, x1, value at x0 is y0, and the value at x1 is y1. Though that is the given data, and we know that constant function will perhaps not work always. You will not always have y0 equal to y1. If you have y0 equal to y1, okay, constant function will work, but most often you will not have y0 equal to y1, and therefore constant function will not work. So what we should then do is to try for slightly above general function, a function which is slightly general than the constant function, and those are the linear polynomials. So these are the linear polynomials which will have a constant term, and it will also have the term involving x. And so they will be written as a1x plus a0. Okay, so this is our polynomial a1x plus a0, and its value at x0 is y0. So we would have that a1 x0 plus a0 equal to y0, and the value at x1 is y1. So we will have a1 x1 plus a0 is y1. Okay, now you know how to solve for this. A1 is not known to us, a0 is not known to us. Other terms are known, x0, y0, x1, y1, these we know. And using these we can solve. You can just consider, so these are two non-homogeneous linear equations, okay? And we want to solve in two unknowns because a1 and a0, these are unknowns. So we can solve this. What you can do is that you can subtract the first equation from the second. Then the a0 terms will get cancelled. You will have a1 into x0 minus x1 is y0 minus y1. And that gives you that a1 is y0 minus y1 upon x0 minus x1. The value of a1 can be obtained readily. Put this value back and then solve for a0, or you can use the same equations, multiply the first one by x1, second by y1, x0, and then take the differences. Now the a1 term will get cancelled, and you again get the formula for a0, which is y1 x0 minus y0 x1 upon x0 minus x1. So there is a linear polynomial that will work, and we know this, meaning we have been learning this from the school, that whenever you have 2 points on the plane, you can join them by a straight line. There is a unique line which passes through these two distinct points. So that we get. This is the interpolating polynomial, which I will write in a slightly different way. I am going to write it as x minus x1, x0 minus x1 into y0 plus x minus x0 upon x1 minus x0 into y1. This is how I am writing it. And the only thing that we have required here is that x0 and x1 are not the same points, because we need to divide by x0 and x1, x0 minus x1. But we have noticed that these were 2 points. I had started by saying that we have 2 points, x0 and x1, so they are not same. And so I can indeed divide by their differences. Okay, so this is the thing that we have, and now we want to generalize this problem and its solution in the coming slides. So let's again notice something here. When we wrote this polynomial, the interpolating polynomial, if your y0 was 0 and y1 was 1, then the first term before the plus sign will not come. You would only get the second term, which is x minus x0 upon x1 minus x0. You are going to get only that particular term. When y0 is 0 and y1 is 1, we got that particular polynomial, which is x minus x0 upon x1 minus x0. Indeed, if you put for that part, if you put x equal to x0, you are going to get x0 minus x0 in the numerator itself, which gives you 0. Whatever the denominator be, the function value is 0. And if you put x equal to x1 there in the second part, you get x1 minus x0 upon x1 minus x0, which gives you 1. So this very special problem, we have a general problem here, which is that x0's value is y0, x1's value is y1. That's a general problem. But suppose we take two special cases, which is that x0's value is 0 and x1's value is 1. Then this second part after the plus sign and without y1, that will work. Or if you take x0's value to be 1 and x1 value to be 0, then the first part, which was the coefficient of y0, that will work. And after having solved these two special problems, you get the general problem by simply multiplying each of those polynomials by the corresponding values, y0, y1, and so on. And this is the trick that we are going to use in our next slides. So this is the problem for us, that we have x0, x1 up to xn. These are distinct n plus 1 points. We have learnt our lesson that the points will have to be distinct. We may have to divide by their difference. And suppose there is a function defined in some way which takes the value y0 on x0, y1 on x1, dot dot dot, yn on xn. Okay, so we have distinct n plus 1 points and we have been given their values. The values can be same. We have no worry with that. We have no problem with that. Actually, we are not going to worry about these values at all. We will want that the points be distinct. So there are these n plus 1 distinct points and then there are these values. We want to find a polynomial p with the property that pxi is yi for I equal to 0, 1, 2 up to n. This is what we want to do. And as I told you earlier, we will solve j special problems. So yeah, I should have said n plus 1 special problems, because at each point for each j from 0 to n, we will have a special problem which takes value 1 at the jth point, xj, and 0 elsewhere. So those are the special problems. So this j needs to be replaced by n plus 1 here. Okay, where yi are delta ij. So delta ij is the Kronecker delta function, which has this property that delta I comma j has the value 1 when I is j and otherwise it has the value 0. Okay, so we want to find polynomials Lni with the property that Lni xj is delta ij, which is 0 for I not equal to 1 and 1 for for 0 for I not equal to j and 1 for I equal to j. Okay, so for each j we should find these polynomials. All right, and so these are going to be n plus 1 polynomials because I runs from 0 to n. Maybe even what we should perhaps have is ln j and xi inside. So I will make those changes in this slide. For a fixed I, ln I of xj 0 for j not equal to I. That is the property that ln I should have. Okay, so once you fix an I, we are fixing this I, and so there is this polynomial Lni. The n is there only because we have n plus 1 points. If you have fixed an n, then there is no need to carry this n around. So don't worry about this n too much, but we are looking at this polynomial Li, which vanishes on xj. And for polynomials, we have a very nice property that whenever a polynomial is 0 on a particular point, then x minus that point will have to divide the polynomial. This is the nice property of polynomials which can be proved using Taylor's theorem. Okay, so x minus xj will have to divide lni for each j different from I. Okay, so for instance, if you had 0, 1 and 2 and you were looking for a polynomial which has the value 0 on 0, 0 on 1 and 1 on 2. then the polynomial, because it takes value 0 on 0, it should be divisible by x, and it's also 0 on 1, it should be divisible by x minus 1. So x and x minus 1 both will divide your polynomial, but since these are all distinct points and each of them divide the polynomial, then the whole product will have to divide the polynomial. So your polynomial will be a multiple of this polynomial, the polynomial x minus x naught, because it should be 0 at x naught, x minus x1 also because it should be 0 at x1, dot dot dot. We have gone up to xi minus 1. Then we are not taking x minus xi, because on xi we want the value to be 1. And then we take the I plus 1 and so on up to n. So this is the polynomial which is now guaranteed to have value 0 on x0, x1, x2 up to xi minus 1, xi plus 1 up to xn. What is the value of this polynomial at xi? It will be some non-zero value, because xi is not equal to any of these points. Remember, x0 up to xn are distinct n plus 1 points. So the value of this particular polynomial at xi will be obtained by putting x equal to xi, and we also know that it has to be non-zero because xi is not equal to xj for any other j. So that value is non-zero, and we now, if you divide this polynomial by that non-zero value, then the value of that divided polynomial at xi will be 1. And since you are multiplying this polynomial by some scalar, non-zero scalar, the values at all other xj remain 0. They will not change. So that's the small trick here. So we define ln by x minus x naught, x minus x1 dot 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 up to x minus xn. The ith one is omitted, and you are dividing it by this real number xi minus x naught, xi minus x1 dot 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 xi minus xn. Again, the ith one is omitted. This polynomial will do the job. It will have the property that ln I at xj is delta ij. If you compute ln I at any other xj from j equal to I, you are going to get value 0 because the numerator will give you value 0. At xi, the numerator and denominator are same, so the value is 1. So we would have solved at one go, we have solved these distinct n plus 1 special problems, where for each I, the value is 1 and all others are 0. And once you are done with this, then the general polynomial is found easily by doing the same trick which we have done in problem 1 for 2 points, x0 and y0. So there we had only these polynomials, Lagrange polynomials, and here we have a general set of Lagrange polynomials. So we take y0 ln naught, y1 ln 1 dot 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 yn ln n. So this is our constructive way to find the Lagrange polynomials which interpolate our given function on the given set of points. And we should also do some of the initial cases to check whether these are the same polynomials that we had found. So those initial cases are case 0. You should always try case 0 before going to any higher case. N equal to 0, there is no 1, there is no 2 and nothing else. So you should only get a polynomial which takes value 1 on 0, and that's all. There is no other data given to us. So that's the polynomial which is just 1. And so Px is y0. This is the constant polynomial that we had started with initially. Case 1 is where n is 1. And so we will have x0 and x1. And then we know that our x0, the Lagrange polynomial L1 naught and L11 are given as follows. So we have the Lagrange polynomial L1 naught, whose value on x1 is 0 because the numerator vanishes on x1. And the value of L1 naught on x0 is 1 because the numerator and denominator have the same values. L11 on x1 you get the value to be 1, and then on x0 you get the value to be 0. And then the interpolating polynomial is simply the interpolating polynomial that we had found earlier. Okay, and this is one more case, something that we have not done earlier. N equal to 2, we simply write down these three polynomials L2 naught, which has the property that it is 0 on x1 and 0 on x2, but 1 on x0. Then the second part, which is the coefficient of y1, that is L2 1, which is 0 on x0, 0 on x2, but 1 on x1. And finally, we have L2 2. So this is how we would write down the Lagrange polynomials. We have not had time to do some explicit example in this lecture, but we will surely do such examples in our next lecture, and many more nice things will be seen. So that's where we stop today, and see you in the next lecture. Thank you.